This lecture will cover the material in chapter 4 of the book. Uh, in this lecture we are going to describe the types of forces that we'll be dealing with in this course. Forces can be divided into two main categories: contact type forces, contact, and long range forces. Contact type forces are forces where the object needs to be in contact with whatever it is that is inducing the force onto the object. Long range, as the name implies, well, you don't need contact. For example, force due to gravity or weight is a long range force. Magnetic force is a long range force. Electrostatic force is a long range force. Um, Magnetic forces, electrostatic forces, etc. We are not going to cover at all in 2101. Those will be covered in 2102. So for the purpose of this course, the only long range force that we will consider is force due to gravity or weight. All the other forces will be contact type, and these forces, for example, include spring force, F spring, normal force, friction, both kinetic, static, rolling friction, air resistance or drag. What else? We have tension, T. So these are contact type forces, and I'll describe what we mean by each of them in just a second. This chapter, as you might have found out if you've read through chapter 4, is another descriptive chapter. We are really not going to do any calculations or heavy use of equations at all. The purpose of this chapter is to learn to identify forces, identify our object, the agents that cause the force to be applied to the object, and how to go about treating multiple forces that are acting on a single object. So the process that we're going to follow is identify all the forces that are acting on our object. Now, you need to decide what your object is. You can only have one object at a time. So if a book is your object, a book which is sitting on top of a table, then you consider all the forces that are acting on the book. If your object is a soccer ball being kicked on a soccer field, then you consider all the forces that are acting on the soccer ball. So you need to have one object and identify all the forces that are acting on that object. Once you figure out all the forces acting on the object, we're going to learn how to calculate the net force. So this is a sum of all the forces that are simultaneously acting on the object. You calculate the net force, and the net force will give us the acceleration that the object will have. So once you know the acceleration of the object, then you can go and use your kinematic equations to solve for velocity, displacement. If you need to figure out how long the delta t, etc., how long it takes for the object to, for example, go through certain displacement or certain velocity change, etc., is essentially do what we've done so far using our kinematic equations. So the process is going to be in this order, where you identify forces, calculate the net force, which gives you your acceleration, and then you use the kinematic equations of motion to solve for whatever it is that you're after. So the first step is let's take a look at the different forces that we have, and actually I've posted here a couple of questions. These are questions that I asked my in-class students, so why don't I go ahead and ask you the same questions. Why don't you take a look at the first question here and think about it for just a second. So we have a particle which undergoes an acceleration a while moving from point 1 to point 2. That's the figure on the left hand side. Which of the choices show the velocity vector v2 as the particle moves away from point 2? So if you like to pause the video and think about this for just a few minutes, then you can come back and see if your answer is correct. Now what you need to consider here is, well, we have point 1, we have this first vector v1, and velocity vector a, which is shown here, we know is points in the same direction as the change in velocity vector, because it's the change in velocity vector divided by delta t. So you need to ask yourselves which one of these choices, A, B, C, D, E, is v gives me the correct delta v. Remember, delta v is final velocity v2 minus v1. So which one of these vectors gives me v2 minus v1? Well, a vector like this, so my v2 needs to be pointing in that direction, because now if I do the tip to tail technique for vector subtraction, you see that v2 minus v1 gives me this orange vector here as delta v, and which is pointing, as you know, in the same direction as A, and that's choice C. So C is the correct answer for this problem. And the next question, vector decomposition. What is the x component of vector c? Vector c is shown in this figure here. So once again, if you like to pause the video, think about this for just a minute, then you can come back and tell me, see if you got the right answer or not. What is the x component of vector c? Well, the vector c, you can write vector c as in the ij form if you like. The ij form is 0i plus 3j, right? So the correct answer is none of the above. Vector c has no x component. Its x component is 0. It only has a y component. So I hope you got these two questions right. Okay, let's go back to talking about forces and the types of forces. We normally associate a force with a push or a pull, and that's exactly what it is. Here we have on the top figure, we have Jane, I guess, pulling on a rope which is attached to a block, and this pulling of the rope exerts a force onto the block. This is a pulling force. Because we have a rope as the medium, that is the force here. The block is our object, and in fact the rope is our agent. Whenever you're trying to identify the types of force, as I said, you try to identify your object. Here we know the block is our object. Well, the object, then you need to decide what is the agent that is exerting the force onto our object. Well, in this case, it's the rope. Yes, the rope is being pulled by Jane, but the block isn't in direct contact with Jane. The block is in contact with the rope. So in fact, the type of force here is tension. Whenever you have a rope or a string, then you deal with tension. So here we have tension acting on the object, for example. There's also of course, well, before we go there, I'll describe normal force, etc. down below. Let's move on to the next figure here. We have the block in contact with a spring. So here we have a spring type force, spring force acting on the block. And if the block were not in contact with the spring, of course we would not have a spring force acting on the block. So if you have a plunger which shoots a ball up in the air while the ball is in contact with the spring, then there is a spring force acting on our object, the ball. But as soon as the ball is launched, then there's no more contact between the plunger and the ball, so the spring force no longer acts on the ball. So here's the object. So there is a spring force, F spring, acting on the ball, but as soon as the ball leaves the plunger, starts moving up, then F spring is 0 because there is no contact between the ball and the spring. So make sure that for contact type forces such as spring force, tension, friction, you do have contact between the object and the agent. The only force that you do not need contact in this course anyway is force due to gravity, which is or weight, which is the long range force. So every other force you have to make sure that there's contact between the object and the agent. Now remember that force is a vector, so if you have more than one force acting on an object, so here we have F1 and F2 acting on our box here, and the net force is going to be a vector sum of the two forces. Now as I mentioned on lecture 1, we are going to deal with a particle model here, so whether you have a box or an elephant or a car, we can represent our object as a particle, a dot. And if you were to draw your XY coordinate system, you place the object at the origin of the coordinate system and then go ahead and draw the forces acting on the object. So this would be our F1 and this is F2 acting down. Now in your coordinate system you can do your vector sum of the two forces using whichever technique you like, whether parallelogram technique or decomposing the vectors and doing the vector algebra, and you would end up with F net, which is the sum of the two forces acting on the object, as shown in this figure here. So do remember the vector nature of the force, and that you would need to use vector algebra for calculating the net force acting on any one object. Let's talk about the spring force a little bit more. Now spring force, in these two pictures I have my object, which is the box, in contact with the spring, therefore there is spring force acting on the object. However, depending on whether my object is compressing the spring or stretching the spring, the direction of the spring force will differ. So if the spring, if let's say this is the natural length of the spring right there, if the object is compressing the spring, then spring force will be towards the object. And once again, this is the natural length of the spring. If this object is stretching the spring, then the direction of the spring force will be towards, away from the object. So watch out for that. And also we are going to, in a couple of chapters time, we're going to see that the magnitude of the spring force is going to depend on how much the stretching or compression is. So the more stretching or the more compression you have, the greater the magnitude of the spring force. But don't concern yourselves too much with that for the time being. We will cover it in a few chapters time. The purpose of this chapter is really introduce the types of forces, and for you to get a hang of identifying these forces and practicing what we call free body diagrams, which are stuff like this. This is called the free body diagram. Tension, whenever you have a rope, string attached to an object, you have a pulling force acting on the object, and that's what we call tension. Now tension always acts along the rope or the string. Okay, please do remember that. So if this is the object, this is the rope, that's the direction in which tension is going to act. So whatever the direction of the rope or the string is, the tension will be in the same direction. And what else about tension? Oh yeah, if you have an object and you have a rope and then you have a pulley system that kind of makes the string meander any which way, then the tension will of course follow the direction of the string or rope and will have the same magnitude throughout. So the tension in the string does not change from the magnitude of it doesn't change from one end to the other, and however it meanders through your pulley system doesn't really matter, but where it makes contact with the object, whatever the direction of the rope is, that's the direction in which tension is going to act on your object. Normal force, whenever you have contact between two objects. Here we have Jane again. Jane is pressing against the wall with the palm of her hand. The palm of her hand is in contact with the wall. If we say that Jane is our object, then there's contact between the object and the wall, so the wall becomes the agent. So Jane is the object and the wall is the agent, and the type of force that you have here is called a normal force, which we show with a little n. So whenever two objects are in contact, we have a normal force. Now normal force is always perpendicular to the plane of interface between the two objects. So if you consider a book sitting on top of a table, the interface of course is here, and our normal force, if we call the book our object, so the book is our object and the table becomes our agent. There's contact between the book and the table, therefore that means there's normal force between the book and the table, and normal force will always be perpendicular to the interface between the two objects, and it will always point towards the object. Okay, so it's always perpendicular to the plane of interface and points in the direction of the object. If we were to switch around and basically ask ourselves what is the force acting on the wall, so if we now make me change the color of my pen, if I make the wall my object, now Jane becomes the agent. Now there's contact between the wall and Jane, and in this case the normal force will be this way towards my object, which is the wall. So that's the normal force due to my object, the wall, being in contact with the agent Jane. Friction. Friction is a type of force that exists whenever there is contact between two surfaces. So the surface of an object and the agent, and its magnitude depends on the roughness of the surface. If you have, and its direction is always in the direction which is parallel to the interface. So it's orthogonal or perpendicular to the direction of normal force. So here we have the sled and the snow. The plane of interface, of course, is here. As you can see, friction force is parallel to the interface between the sled and the snow. In this case, our object is defined as the child and the sled together. There's contact between the snow and the sled, of course, and if the object is moving with respect to the agent, here obviously it is moving because a velocity vector is shown, we have what we call kinetic friction. Okay, and the direction of kinetic friction is always opposite that of motion. Here velocity is to the right, so the direction of kinetic friction is to the left, and it is parallel, it's essentially parallel to the surface. If the object is not moving, is stationary, for here we have the froggy sitting on a slope, what we have is static friction between the object, which is the froggy, and the slope, and the static friction is the force that keeps the frog from sliding down. And once again, the direction of static friction is opposite, is in a direction such that it would oppose motion. So here, if there were no friction, the frog would start moving in downwards, down the slope. That's why the direction of static friction is the way it is, up the slope. Kinetic friction is shown in this book using a little f with a k subscript, and static friction is shown with f subscript s, static friction. We're going to cover this in the next chapter, but let me just give you a little brief preview. The magnitude of kinetic friction is given by normal force times coefficient, and this coefficient is a number between 0 and 1, coefficient of kinetic friction. And static friction, its magnitude depends on how much force there is acting on the object. However, it does have a maximum magnitude, which is given by n mu s, coefficient of static friction, and coefficient of static friction is always greater than coefficient of kinetic friction, but we'll cover this fully in chapter 5. Air resistance or drag is also another friction type force, and just like kinetic or static friction, its direction is opposite that of motion. So here we have leaves falling from a tree. They're of course moving downwards, therefore drag is pointing upwards. So if you have a baseball which is hit like this while the ball is in motion here, air resistance on it is this way, while the ball is here moving that way, and the air resistance acting on it is this way. So this is drag, drag, and the black arrows are of course the velocity vectors for the ball. So its direction is directly opposite that of motion. And finally we have, not finally, pre-ultimate forces, F thrust force. That's the force due to a rocket engine, jet engine, and its direction in this case of course is the direction in which it's going to accelerate the rocket forward typically. But if you have a scenario where we have a rocket with F thrust this way, but we also have, so this is F thrust, we also have weight acting on it, well the net force is going to be this way, so this is F net. So F thrust if you have other forces acting on the object, may not necessarily be in the direction of the acceleration. And finally, our long-range force, weight, force due to gravity, that always points towards the ground. So that's a simple force to figure out. And you don't need to have contact. This is the only long-range force that we'll be dealing with in this course. Alright, one more time. Force, to review the vector nature of force. So here we have a box as our object, which is being yanked by two people, and we have two ropes attached to the box. Therefore we have tension 1 and tension 2 acting on our box. What you will need to do is do a free body diagram for the box. Draw your Cartesian coordinate system, x and y. Show your T1 and T2. Well, you first of all show your box as a point at the origin, and then draw your T1 and T2 as two vectors which are consistent with the forces T1 and T2, both in terms of direction and magnitude, of course, and then calculate Fnet. Fnet either using the parallelogram technique, vector algebra, whichever method you care. And once you figure out Fnet, then the acceleration vector will point in the same direction as Fnet. Acceleration vector and Fnet have the same direction. So that's the process that we are going to follow really for the remainder of this course. So identify your forces. Let me change the color of my pen. Identify your forces, calculate net force, and then that will give you your acceleration. I just showed you how to figure out the direction, but the magnitude of acceleration you can also figure out. Newton's second law tells us that net force acting on an object is directly proportional to the acceleration of the object, and that constant of proportionality is what we call mass or inertia of the object. The units, of course, are kilogram in the SI units. So having figured out your net force, it's a trivial matter to calculate acceleration. Do remember that we're we may be dealing with more than one dimension, so you may have to calculate net force along the x direction, net force along the y direction, which in turn they will lead to acceleration along those respective axes. Now you can recombine AY and AX to get your final acceleration vector, both magnitude and direction, of course. Newton's second law, if you were to do an experiment and plot acceleration A versus force, you will end up with a straight line, of course, and here what we have is acceleration is equal to net force divided by m. So the slope of the line is 1 over mass of the object. So if you have if you now double the mass of the object, you'll end up with a line which has half the slope. So here we have 1 over m2, so this was m1, let's say. So m2 has double the mass, so its slope is 1/2 of that of the orange line. So which makes sense, because for a given force, if you have a mass with twice, if you have an object with twice the mass, you're not going to accelerate it as much, of course. And if you were to have the mass, well, you'll double the slope. So So this is 1 over m3. So now for a given force, you'll have a greater acceleration if your mass were smaller, of course. So if you were to do an experiment and plot acceleration versus force, I believe there is such an experiment in your labs, then you'll end up with straight lines whose slopes are inverse of the mass of the object. The units for force are newtons, which are same as kilograms meters per second squared. Okay, so rather than writing kilograms meters per second squared each time, we go with newtons. So the weight, for example, of an object is defined as its mass times acceleration due to gravity, g, and let's say that we have a 10 kilogram box, and multiply that by acceleration due to gravity, which is 9.8 meters per second squared. So therefore the weight or force due to gravity acting on this 10 kilogram box on the surface of the earth is 98 newtons. Okay, that's the weight of a 10 kilogram box, 98 newtons. What I'd like to do now is to get a little bit of practice doing free body diagrams. Let me see what I have here. Alright, let's do take a look at some free body diagrams, how to go about doing free body diagrams. The first step is force identification. So here we have a person in an elevator. The elevator is supported by a rope. So what you may want to do is go ahead and draw a boundary around your object. That's that red line around the object. I'm looking at the figure on the left hand side. Once you draw a boundary around the object, then think about all, go ahead and identify all the contact points that your object makes with the outside world. Well, there's only one contact point here with the rope. So that's if there's a contact, that means there's a force. Now, what is the object in contact with? Well, it's in contact with the rope. That means the type of force that we have is tension. Okay? And after you've identified all the contact forces, go ahead and say that, alright, then, oh, I'm sorry, let me go back. If you have tension, then you know that your tension is acting in the direction of the rope, so you can actually give a direction to your force as well. And then finally, go ahead and add your weight vector, which is always pointing down. So that's your W, that's your long range force. Now that you've identified all the forces acting on your object, which is the elevator with the person standing in it, which only have two forces, tension and weight, then you do your free body diagram. To do a free body diagram, as I said, draw your Cartesian coordinate system, place your object as a dot at the origin, and then draw each vector. So you draw the vectors. Here we have tension, which is acting upwards, and we have weight, which is acting downwards. Okay. And once you draw those to scale, problem may tell you what each one is. Then you can calculate the net force. That's the net force, which is a simple vector subtraction in this case. T minus W, because why T minus W? Net force, or sum of all the forces, in this case we only have the Y direction, so that's Fy, is tension, alright, minus W. Why minus W? Because W is pointing down, away from the positive of the axis, that's why it assumes a negative number, and tension of course is pointing up. That's positive. So my net force then becomes T minus W. So that's my net force. And in this case, the way I have it in the drawing, my net force is pointing up towards the positive of the axis, which means that there will be an acceleration in the upward direction as well. So the elevator will be accelerating upwards given these conditions. So that's the process that we go through in drawing free body diagrams. So let's get a little bit of practice doing these free body diagrams. Here we have a scenario. We have once again an elevator being supported by a rope, and we've also been given a motion diagram. In the motion diagram, as you can see here, the velocity vector is increasing downwards, which implies there's an acceleration downwards. Okay, so how do we go about constructing a motion free body diagram in this case? Once again, do your coordinate system x, y, place your object at the origin of the coordinate system, and what do we have? We have let's identify our forces now. Here's the boundary around our object. There's contact at this point. The contact is with a rope. That means there's tension, and tension is in the direction of the rope. That's our T. There's no other contact with anything else, so let's just also add our W, weight. So tension up, W down. Now go ahead and copy those forces onto your free body diagram. Tension up, okay, and W down. Now when you draw W, notice, pay attention to this. We need an acceleration. The acceleration is downwards. If the acceleration is downwards, that means that net force, F net, must also be downwards. So when you do the sum of the two forces that you have, in this case we only have tension and W, we need to end up with a net force which is downwards. That's why I go ahead and draw my weight vector W longer than T, because now when I do F net, two forces, I have T minus W. Notice that if W is longer than T, then I'll end up with a negative, in this case, negative F net, basically. F net will be negative in value pointing downwards, and which means that I have an acceleration downwards. So do pay attention if the problem gives you a motion diagram and the acceleration vector, then that's the direction in which you want to end up with your net force pointing. Okay, here we have a car going down a slope, and the motion diagram shows that the car is slowing down. The velocity vector is getting increasingly smaller, so we have an acceleration upwards. The direction of motion is x. Okay, so let's identify our forces first. There's a boundary around our object. Well, the car makes contact with the ground, so that means that there is normal force acting on the object, which is the car. There's the car is moving in a downward direction, which means that there is some friction force acting on the car. Okay, now in this picture it shows it as a kinetic friction, but strictly speaking it's a static friction, because if the tires are not skidding, then at any given time as the tire rotates, the part of tire in contact with the ground is in static contact with the ground. But that's a detail that we'll cover fully in future. But right now let's just call it a friction type force. And what else do we have? These are the only contact forces there. There's no rope attached to the car, so nothing else. And the other force, of course, is weight, which in this case will be acting downwards. So that's our W. So now let's do a free body diagram. To do our free body diagram, we need to draw our coordinate system, and I'm going to draw a tilted coordinate system. Why? Because my x direction, I'm sorry, I didn't mean to do that. The x direction, all right, This X direction is pointing down, so that will be my X direction. This is in my Y direction. Now copy the forces onto your free body diagram. So we have normal force acting along Y, we have friction acting in negative X direction, and of course we have W acting down. Okay, so now let's see if this is consistent with acceleration acting up the slope. If acceleration is acting up the slope, that means my F net will also need to act up the slope. Now, if that's the case, here I have 3 force vectors. So let's take a look at the sum of the forces in the X direction first, and then the sum of the forces in the Y direction next. So what are the sum of the forces in the X direction? Well, I have in the X direction, the first force that I have is F. It's pointing in the negative X direction, so that's minus F. And then the other force that is acting along the X direction is the X component of W, Wx. Okay, so that will be plus X component of weight. So if you know the slope, if the slope were 10 degrees, for example, okay, if you know the slope, then you can go ahead and calculate what the X component is. That would be W sine of theta, for example, okay, for Wx. Now in the Y direction, what do we have? We have normal force acting up, and then we have the Y component of W, Wy, but it's pointing downwards. This would be minus Wy, which is actually given by W cosine theta. Okay, so this is how you go about doing your free body diagram and calculating the net force in both X and the Y directions. Now in the Y direction there is no acceleration, so we know that the sum of these forces must equal 0, because if the net force in the Y direction did not equal 0, that would mean that there is acceleration in the Y direction due to Newton's second law, F equals ma, or acceleration is net force divided by mass. But we know that there isn't any acceleration, therefore the net force in the Y direction must equal 0. But in the X direction, there is acceleration. It's a negative acceleration, and sure enough, if you take a look at F minus F plus Wx, you see that we end up with a vector which is negative, because F is longer in length than Wx is, if you look at the drawing. So we'll end up with a negative vector, which is consistent with the acceleration being, or net force being pointing in the negative direction, which in turn means that the acceleration vector is pointing in the negative direction. Right. What about a flatbed truck carrying a crate? And let's say the crate is our object here, and we've drawn a boundary around the crate. And what are the forces acting on the crate? Well, here's W acting down, and the crate only makes contact with the flatbed of the truck. So there are 2 forces. One of them is a normal force acting towards the crate, and the other one is static friction, right? The crate isn't moving with respect to the truck, no, hopefully. So the static friction is the other force, but the question is, which direction should we point the static friction? Well, before I give you the answer, let's take a look at the free body diagram here. What's happening to the truck is the truck is accelerating. Okay, so the crate is accelerating forward. So if we now do a free body diagram for the crate, this is X and a Y. Let's put the two forces that we identified. There's weight downwards and upwards. By the way, there is no acceleration in the y direction, so that means that magnitudes of n and w must equal each other because they cancel each other. The net force in the y direction is 0. But now let's consider the x direction. The free body diagram for the crate says that there is acceleration forward, which means that there is net force, right? Net force in the x direction, in the forward direction. And the only force in the x direction that we identified is that due to static friction. Therefore, static friction must be this way, Fs, because that's the force that essentially gives you your net force in the x direction, which in turn accelerates the crate forwards. Now, let's do a little sanity check, ask ourselves if this makes sense. Well, if there were no static friction, which way would the crate move with respect to the truck? Well, it would move backwards, right? If there were no static friction. So if it were to move this way, then static friction is in a direction to oppose that motion, so it is in the forward direction, so that makes sense. The sanity check holds as well. One other similar example to this is that of a bag of groceries sitting on a car seat, and the free body diagram here for the bag shows that it is slowing down. So obviously we're approaching home and we're applying the brakes, and the car is slowing down, which in turn slows down the bag of groceries. So how do we go about doing a free body diagram here? We've drawn the boundary around the bag of groceries. Our forces, well, there's weight, which is acting down, weight. There is normal force between the bag and the car seat, which is acting in the up direction, and of course our friend static friction. Okay, so once again, before I give you the answer, let's do the free body diagram. This is the origin, that's the xy coordinate system. W is acting down, normal force is acting up. Once again, there is no acceleration in the y direction. AY is 0, which means that the sum of the forces in the y direction must be 0, and the sum of the force in the y direction, we have normal force minus W, which in turn means that N must equal W. So normal force must equal W in this case. Now in the x direction, notice that we have acceleration A, which is pointing in the negative x direction, i.e. F net in the x direction must point backwards, and the only force in the x direction that we've identified is that due to static friction, so our static friction must point in the negative x direction. Okay, and it's this force that leads to the grocery bag slowing down. Okay, so having said that, let me ask you this question here. If you were to take a look at this free body diagram and think about whether the object is slowing down, speeding up, or moving at a constant velocity. Alright? So take a look at the drawing. We have weight, normal force, friction, and by the way, net force, always put it to the side of the free body diagram. Don't show net force kind of starting from the origin, because it's not a real force acting on the object, it's just the sum of all the forces that you have. So a net force is not a separate force, it's just the sum of all the forces that you have acting on the object. So kind of indicated to the side, which in turn gives you your acceleration vector, of course, at least its direction. and its magnitude, as you know, you can figure out by using the Newton's second law, F net divided by m. Anyhow, let's go back to the question. Let's go back to the question, and let's we'll think about whether the object in the drawing is slowing down, speeding up, or going at constant velocity. If you like to pause now, please go ahead and do so. Now, to find the answer, first of all, pay attention to the fact that F net is in the positive x direction. That means the object has an acceleration in the positive x direction. Okay, so the object has an acceleration in the positive x direction. So if only we knew which direction the object were moving, then we can figure out if it's speeding up or slowing down. To figure that out, pay attention to this. We're dealing with kinetic friction, and kinetic friction, as we said before, always points in opposite to the direction of motion. That means that the object has a velocity vector pointing in the negative x direction, since kinetic friction is pointing in the x direction. So the object has velocity pointing in the negative x direction, acceleration pointing in the positive x direction, which in turn means the object is slowing down. Okay, because the velocity vector and the acceleration vector are opposite to each other in direction. So now let's take a look at this free body diagram on the right hand side. And here once again we have normal force, weight, we have a spring force. So obviously there's a spring attached to our object, and kinetic friction. Okay, now if I were to do a drawing of this, this would be spring like this. Now, is my spring stretched or compressed? Well, it is stretched, because if I do a drawing like this, it is stretched because the spring force is acting away from the object, and the object sits on the floor. Why? Because I have kinetic friction. So kinetic friction is acting this way, which implies that the object is moving this way, right? So that's the velocity vector of the object. So my object has a velocity vector that way. But now take a look at this. F net is also towards the negative of the axis, which means the object is also accelerating in the negative x direction. So it's moving towards the negative x and has an acceleration vector pointing in the negative x direction, i.e. the object in this scenario is speeding up, because the acceleration vector and the velocity vectors point in the same direction. Alright, let's think about this little problem. In which direction does the object accelerate? So here's the question. Alright, so if you like, you can pause the video again. Now, to figure out the answer to this problem, well, we need to do a vector sum of f1, f2, and f3, because vector sum gives us the f net, and f net defines the direction of acceleration. We had f1, f2, f3 doing a vector sum. If we do a vector sum with, of f1, f2, that gives us this diagonal vector right here, and then do another sum that gives us the sum of f1, f2, and f3. So this is our f net. So obviously our acceleration vector must point kind of in a southwesterly direction, looking up in our choices. That's choice consistent with choice D up here. I hope you got this question right. Alright, let me ask you, well, actually before we do that, let me mention equilibrium. I'm just going to introduce equilibrium. We'll leave doing problems involving equilibrium till the next chapter. The definition of an object being in equilibrium is when the net force acting on the object is zero. When net force is equal to zero, that implies the acceleration of the object is zero. If we're talking in terms of a two-dimensional motion, then if a acceleration is zero, that means ax and ay are of course zero. There are two types of equilibrium. Equilibrium comes in two flavors. One is static equilibrium. That's when the velocity is also zero, i.e. the object is stationary. Second type of equilibrium is dynamic equilibrium, in which velocity is not zero but is constant. Remember, acceleration is zero. So in the two diagrams, the policeman standing still has a zero velocity and zero acceleration. The policeman is in static equilibrium. There's no force acting on no net force acting on the policeman. Here the teenager on the skateboard is moving at constant velocity to the right. His velocity is not zero but acceleration is zero. Once again, net force is zero on the teenager and the skateboard, and he's in dynamic equilibrium. So that's the definition of equilibrium, and we'll do problems involving both static and dynamic equilibrium in the next chapter. I think we introduced all our forces. We practiced doing free body diagrams. Please read through chapter 4. It's a fairly straightforward chapter to go through. Important things to remember are that you need to know, first of all, what is your object. Identify your object, and there's only one object that you have to have at any time. Do not mix and match objects. So identify your object, whether it's a box, a car, an elephant, a bird, whatever it is. Know what your object is, and then identify the contact points that it has. With the outside universe, and at each contact point you will have a contact force. Okay, and you identify the contact force by the agent causing that force. So if the contact is with a rope, then you're dealing with tension. If it's a floor, then you have normal force. If it's well, you also have friction if it's in contact with the rough surface, etc. And then add your long range force, which is weight. All right. So once you identify all your forces, then you do your free body diagram. The free body diagram, I hope you know what it is by now, is a tool to enable you to calculate the sum of all the forces acting on the body. So you do a net force calculation. When you do a net force calculation, that in turn, using the equation F, sum of all the forces divided by mass is equal to acceleration, that in turn gives you the acceleration that the body experiences. And do remember that if you are dealing with a two-dimensional motion, then you will end up with the AX and AY, acceleration in both X and Y directions. And then you go ahead and use your kinematic equations, equations to figure out whatever it is the problem is after. Alright, so please do remember this order in which you need to go about solving these problems. I think that's about what I have to share with you. So I'll post these notes today, and you'll have homework due, well, posted today, due next week. Have a good weekend. Actually, I just remembered something else that I want to share with you. So if you bear with me for a few more minutes, I'd really appreciate it. Now, um, is the first couple of chapters we learned how to do graphic analysis. The graphic analysis where, for example, we had, let's say, velocity versus time. We had a plot like this, and we were after displacement, and displacement was the area on the velocity versus time plot. And if we had acceleration versus time, which kind of looked, I don't know, something like that, for example, then change in velocity was the area under the acceleration versus time plot in between two limits, okay, whatever limits the problem specified. And if you recall, dx dt slope, the derivative of position with respect to time gave us velocity, and dv dt gave us acceleration. Well, um, uh, remembering these, if we now go and combine Newton's second law, for example, well, first of all, let's do this little exercise here. Let's say we have a mass of half a kilogram, an object with a mass of half a kilogram, and we are given acceleration versus time plot for that object. So here we have an acceleration versus time plot for the object. If we were to draw force versus time, how would we go about doing that? Well, Newton's second law says that force is equal to mass times acceleration. Okay, so converting this plot to force versus time is a simple matter. All you have to do is multiply acceleration by mass in kilograms, alright, units of kilogram, and you'll end up with force in newtons. Okay, so it's a half a kilogram, so multiplying 1 by a half, you end up with a half there. This would be 0.75, so it would be 0.25, 0, negative 0.25, and this would, the units of course will be in newtons. Alright, so and the time scale remains the same, so we can convert an acceleration versus time to force versus time simply by changing your vertical axis using Newton's equation here. And conversely, if you have a force in newtons versus time in seconds, and once again the mass is given as half a kilogram, and let's say the problem asks what is the change in the velocity over the period 2 to 3 seconds. Okay, so what is that? So this is the period of interest from 2 to 3 seconds. Well, we're given force versus time, but to calculate change in velocity, which is delta v, remember change in velocity is the integral of acceleration curve over the limits that you have. Integral of the acceleration versus time curve is the area under the acceleration versus time curve, of course. So we need to convert our force versus time to an acceleration versus time curve. Now we do the reverse operation. If we divide force by mass, then we get acceleration. This is force in the x direction, we'll get acceleration in the x direction. Okay, so if I were to divide, let me get rid of this circle there. So if I were to divide force by mass in kilograms, I get my acceleration in the x direction. The units would be, of course, meters per second squared. So 1.5 divided by a half, that's 3, 2, 1, 0, minus 1. Now let's do the area on this region here from 2 to 3 seconds. That's the blue shaded area, which has a height of 3 units, 3 meters per second squared, multiplied by 3 minus 2 is 1 second, so that's 3 meters per second, i.e. change in velocity in the x direction of the object due to this force acting on it is 3 meters per second, from 2 seconds to 3 seconds. Okay, so over the interval of 2 seconds to 3 seconds, the velocity of the object changes by 3 meters per second. All right, and should a problem, let me open up some space, should a problem give you let's say two plots, let's say there's fx versus time. All right, so we have fx versus time that looks like that, for example, and then fy versus time. So there are two forces acting on the object, one along the x direction, one along the y direction. Let's say fy acts like that. All right, from you convert each graph to an acceleration ax versus time by dividing force by mass, of course. Okay, the shape will remain the same, but the scale will change, and here you'll end up with ay divide, oh, that's a very funny y x-axis there. Let me get rid of that if I can. Okay, my screen is locked up on me, so just bear with me 1 second. Doesn't want to change. Alright, let me draw it again. T. So the shape doesn't change, but as I said, the scale changes because what you do is simply divide the force by mass. Okay, and now if now that you've determined ax and ay versus time, you can go ahead and calculate, for example, change in velocity x by looking at the area under the curve here. So if you're interested in change from 0 seconds to whatever it is, 5 seconds, for example. So delta Vx is given by the area under ax dt. And you can calculate delta Vy in a similar manner by looking at the area under ay dt. Alright? Let's see, why doesn't my eraser work on this crooked line? Doesn't want to erase. Alright, that's alright. The line wins, I lose. Now that you've figured out change in the x velocity and change in the y velocity, now you can do a vector combination to get the change in velocity vector. How do you do that? Well, draw your Cartesian coordinate system. Alright, that's your x, that's your y. You just calculated delta Vx, so let's say delta Vx is a vector like that, that's delta Vx. And you also calculated delta Vy, which is a vector like that, delta Vy. Alright, now delta V is the sum of the two vectors. Alright, so that's this vector right there. So that's your delta V. Alright, so delta V, you can use the Pythagorean theorem to figure out the magnitude of delta V, which is the square root of delta Vx squared plus delta Vy squared. We covered all this material before. And also you can specify the angle that delta V makes, for example, with respect to the positive x-axis by doing the inverse tan of, in this case, delta Vy divided by delta Vx. So starting from force versus time curve for both in the x and the y directions, you figure out acceleration versus time in both x and y directions. So it's the same process, but you just do it twice. And from these acceleration versus time curves, you figure out changes in the velocity both in the x and the y directions, and then you do a vector combination. Use your Pythagorean theorem to get the magnitude of delta V, and use the your trig function to get the angle that it makes with respect to the positive x-axis in this case. Okay. What else did I want to share with you? I think that's about it. So once again, please do read the material in chapter 4 to be and if you have questions, you can either email me. I still Want to encourage you guys to participate in the online discussion sessions. I have one session Tuesday mornings from 10 to 11 and one session on Thursday afternoons. I believe it's from 3 to 4. I really do urge you to participate in those, and also do attend the SI sessions, supplementary instructional sessions, which are held Monday through Thursday each week from 9 till 5 in Burson 137. I myself am there every Monday and Wednesday from 10 to 11 a.m. But there's always a faculty member and TAs there available to assist you with any problems you may have. Okay.